All right, Adam, this is Patrick Gallagher. Adam, how are you today?
Doing great. How are you?
I'm doing okay. I just wanted to welcome everybody to Dev Network's Developer Week webinar series. I'm Patrick Gallagher, and I'd like to welcome all of you to this week's featured webinar presented by Lightstep. Lightstep is a regular sponsor of Developer Week events, delivering unified observability with visibility across multiple layered architectures, enabling teams to detect and resolve regressions quickly, regardless of system, scale, or complexity. So before we get started with Adam's presentation, I just wanted to remind everybody that everybody can participate via live chat. There's a question in the live chat right now. What's your quarantine go-to song? So go ahead and throw some information in there. We want to check out what everybody's listening to and keeping themselves pumped up during the normal or abnormal work weeks. And so make sure you throw in some information in the chat as well as add in your questions for Q&A. And we will be covering Q&A at the end of the session. The Q&A and chat is to the right of your viewer, and you can click on either one to give us information. Also, the webinar will be recorded and made available within the next 24 to 48 hours for additional viewing, or reviewing, I should say. And you can also send it off to your coworkers so they can check it out. So without further ado, let's talk about our presenter today, and that is Adam Johnson, Senior Solutions Architect at Lightstep. Adam currently works with customers to find purpose-built solutions that fit their specific needs and ensure that they can get started getting value from Lightstep and their observability data quickly. Adam has spent his career working in open source tooling and navigating the internal question of when to build versus buy software. He spends his free time reading fantasy novels in San Francisco with his wife, Kim. So without further delay, I'm going to get off and I'm going to throw it over to Adam.
Great. Thanks for that great introduction. So today I have an intro slide now, and I feel like that's even redundant, but I'm going to be talking about whose fault it is when Kubernetes breaks and some different methods we can employ and start researching when these deep and complicated systems break, whose fault it is, who can fix it, and how we can start quickly getting answers from that. So my introduction slide, I think everything's been said, but this is my first all virtual conference that I've had since quarantine. I'm used to being in the conference circuit and standing at a booth and giving talks and living in hotels and eating bagged lunches. So hopefully everyone is much comfier at home and eating a bit better. But glad to see that this is still alive and well. So first, just kind of looking at a high level, again, we're going to be looking across like why we're running Kubernetes, when problems go wrong, who's to blame, where we can look for individual problems, and how we can start getting solutions more quickly, specifically by looking at the tooling we're using and how we're looking at these problems. So first on to why we're actually running Kubernetes. A lot of almost every monitoring discussion or platform discussion begins with the tools that you're running, and there's a million tools and a million vendors to solve all of these different problems. But what is really interesting about the tools that you have and use is they actually control your view of the world and what levers you have available. So if you're someone that's very versed and operating very heavily in the Kubernetes management layer, working with something like an ECS or Rancher or GKE, you're very intimately familiar with defining your scale groups, you're defining pod size and instance you're deploying to, and things like that. So that kind of shapes your understanding of how you're able to address and answer problems. And that becomes really critical because when things go wrong, you have the levers available in front of you. And as that may be a very limited view, you may have a ton of oversight, but it shapes your understanding of the problem. So on top of the actual levers you have to fix problems, you have tools that tell you where problems are. And this, you probably have some, we talk about 3 pillars of monitoring being logs, metrics, and traces. You probably have some combination of all of these across your organization. And building a good practice around who goes where when a problem happens and who knows to look for what is very integral and a muscle that I help a lot of customers build and learn how to appropriately do. So again, you now have tools telling you what goes wrong in several different ways, a different set of platforms that allow you to actually fix problems. And the thing that a lot of these infrastructure platforms don't really capture is they're very concerned with abstracting the information or abstracting the running of the infrastructure to make that very simple and easy. But what they don't necessarily care about is what's running on them. It's by design abstracted away. Like, you don't need to know what's being done here. And that's part of the brilliance of it. But that gives us a problem of we now have several different sources of data and several different sets of data, and our levers might not even address the problems. So these tools really do feel like they give us an ocean of data. I know working with a lot of these telemetry tools, when you're looking at a log or metric tool, when you're trying to actually find something that goes wrong, it feels like you're just throwing darts at a wall from 1,000 feet away and trying to have the right set of keywords and guess. A lot of organizations have runbooks that help codify these best practices. When this goes wrong, put this thing in this search bar and see what you get. But it really does feel like you're awash in this giant ocean of data, and you need to really be trained to understand how to utilize that and get value out of that. And while that specific skill is really helpful, the problem that most organizations have is that it's an organization-specific thing. This company organically grew to be able to solve problems within their org, and you as an individual have either worked at previous companies or worked on these same kinds of problems, but this new company has a completely different set of runbooks. So standardizing, fixing Kubernetes is really a difficult and interesting problem, and something that, again, kind of leaves you feeling adrift. What would really be closer to the stream state is having a much more uniform and simple way that you can address problems and really narrow the scope of what's going on. So I'll touch on some more of these concepts a little bit later, but being able to have service-centric views for how you're monitoring, or being able to isolate problems to specific components within the stack versus needing to start investigating the entire system when something goes wrong, or even being able to understand that the levers I have in hand are not good levers to pull in this situation. What happened was a code release, and all I have are scale levers. So scaling up isn't going to fix broken code. The more memory I give it, the more memory it's going to chug. So we want to start isolating our view of the problems in the world into less of a sea of data and more into actual actionable things that a human can pick up and do. So what actually causes this kind of problems and stress within our environments? One of the biggest problems from a human operator perspective is we have visibility into our control plane. We are very intimately familiar with what we are working on day to day. However, the responsibility now becomes exceptionally deep with all of the downstream microservices that might be impacted, with all of the other configs that touching a centralized thing might impact. So the level of control that we have remains fairly static and is a function of our mastery of all of the tools that sit in front of us, which is really reasonably expensive and not necessarily repeatable to build. And what you're responsible for continues to grow, and ideally should continue to grow in the world of quick dev releases and agile cycles where new code can be coming out either daily or, if not, every other week at slower cadences. So very frequently you're sitting on just a massive pile of change, and you need to very quickly be able to understand with your limited knowledge and be as effective as a single person can be. And that's kind of really the crux of this problem, being able to impact the most change while not knowing an inhuman amount of stuff. So one of the major movements in this has been DevOps. So having a nice cliche DevOps slide in this, of course, is a mandatory at this point. But this really has been the cultural reaction to this and trying to democratize the responsibility of maintaining these systems, a kind of an acknowledgement of one person managing something 20 layers deep, likely that's never worked on that individual piece of code, cannot appreciate the complexity or number of systems that it actually touches. So we need to in-build software that monitors all of these systems alongside each of these. So having things like, along with like software tests, being able to mandate that there are metrics or monitors available within a service has been a very standard practice within this, so that anytime you pick up a screen, you have a fairly standard set of data that you can work with, no matter what the service is. There's amazing benefit to this. The interesting thing is when you start doing this in a very uniform way, the industry pattern for this is having agents embedded within your code, and they look for pretty stock things. So you can expect to find the stock things. It's when things that are off that beaten path go wrong, it becomes a little bit more troublesome. But one thing I do want to actually give a plug for is the OpenTelemetry project. OpenTelemetry is kind of a merger of OpenTracing and OpenCensus from a lot of the other large tech firms, Google, Microsoft, Splunk, Lightstep are all very heavily involved in this, along with tons of others. And the real vision, driving vision behind this project is being able to commoditize telemetry data so that you can just release software code and expect that there is the standardized set of data. It's coming to fruition and newer, but it has a ton of activity. And being able to completely commoditize this entire problem space of how do I get data, how do I preserve it, and where do I send it, is really the vision of that. And then we can focus on higher level systems that tell us what went wrong, why things broke, and focus on root cause analysis, as opposed to this mindset of just, we'll give you the ocean, you figure out what to do within it. So that, I think, is one of the more exciting directions that this is taking. But I just wanted to nod, this is how culturally we tend to react to this. And the situations of customers that I normally talk to almost always universally have the feeling of, I get paged for garbage. There's too many alerts that are happening. I just put those into a black hole because I know that one goes off at noon. This one happens at 3. I have automated groups that should deal with most of these things. And I really only care if the autoscale group didn't fix the problem after about 10 minutes. Or if I can just see from the alert, like, everything's down. So again, there's just an overabundance of noise and an overabundance of this machine data that you need to like know what you're looking for to be able to actually get any value out of. And that is a problem for people. It's overwhelming, and what we do with a overwhelming amount of stimuli is shut down and just kind of tune it off. So the other fun aspect of this is just kind of waiting and see what happens. I know a lot of reaction is, let's automate all of these problems away. And it's amazing to see the progress and stuff people can actually do with that. But it's also very difficult to actually get at the underlying breakages that code introduces. I'll steal a little bit from some of the future slides, but one of the major causes for breakage is change. And things like user patterns or daily cyclical traffic are being pretty well addressed by these auto scaling groups and automation, how you're actually handling this. And it is much more insidious when the problem is caused by an internal feature, or there was some dormant bug that not frequently utilized code path now invokes, and this new strain causes an explosion of problems. Again, no amount of auto scaling or even having that perfect metric to scale against is going to address that kind of problem. And those are the ones that can be really insidious and not necessarily have a clear path of resolution. So looking further into things that we can start doing about this, again, automation is a great way to start making strides at this. As I just mentioned, there's imperfect metrics and data to work against when you're doing this. Scaling against CPU and memory are often not useful scale features for a lot of code, especially if you're running something like Java, where CPU will spike during garbage collection. So now you have to start having a pretty intelligent means for handling and detecting garbage detection versus actual like retry loops that you get stuck in. Or memory is greedy. It will always use all of its memory. So that's, again, not necessarily a useful thing against which to scale. So you can, again, get down this hole of finding like the perfect metric, or we're defining a custom thing in Prometheus that we query against. And anytime this fluctuates that way, we think it might be this, so take that action. But again, this is fairly deep down the expertise curve that you need to really build and understand within these systems. And it's really a joint effort between a bunch of organizations. My goal as an individual is to be able to answer these questions really quickly without necessarily having an entire engineering team fix all of this, because they want to be building other stuff. So kind of underlying in all of this is trying to optimize our debugging experience for unknown cases or novice investigators. The ideal would be if we're able to hire an experienced DevOps or operations person that's used to diagnosing and understanding Kubernetes systems. They can come in and say, great, here's what we have, here's what I can determine from this, and I can actually start making meaningful insight without spending months reading your own runbooks and documentation pages just to understand how systems break. So again, touching on this, the three pillars are very core to what our tooling and view of the world actually looks like. Each of these have their own individual strengths, and just sharing how I see organizations actually use this. Metrics tend to be the quickest line of defense because it's just pure data. It's very quick at reporting and getting the very near real-time alerts on when things break. However, these are often have a very horizontal slice to just a specific system. So you're going to be looking at ingress and machine metrics on a single server or service, and it's able to say when that service is experiencing stress, but that stress might not come from that service. There might be upstream, downstream, external forces, and that again becomes the real crux. If it was just this machine has stress, auto-scaling would fix everything. So that there is some limitation with what you can do with metrics. Logs have amazing detail, but it's effectively go look it up in the encyclopedia, and you are overwhelmed by how much data there is. A lot of progress has been made, but it just ends up being such a mess reading through these, especially with multiple machines. The more distributed you get, the harder it is to actually track and understand what's going on in these systems. And tracing has a very full execution context. Historically, there's been a lot of trouble with the amount of data that this has, because you effectively have a one-to-one request to trace production. So it has just again, a ton of data, and historically it's been very expensive to do. No one wants to instrument their code entirely. So there's been evolutions in each of these. Again, just coming down the list, one of the most powerful things that I've seen a lot of metric systems doing is creating aggregate or compound metrics or summary metrics that are a combination of several things. If you have a data scientist somewhere in your team, this is probably something they love doing, just in terms of refining features that are actually meaningful. So you can reduce several important factors down to one signal that actually means something very specific. The great thing about that is you can now start having metrics that result to explicit resolution patterns. But the challenge is this requires a really intimate knowledge of your system, and you need to be able to actually pick and refine. And this is a pretty full-time job. And people often don't want to spend their entire day job looking at this one thing or refining this perfect system to resolve, because next week we might have a different set of software that's running and this metric's invalidated. So it just really creates a lot of TLC doing this perfectly, but there is promise there. Log tools have been better and better refined. Using Splunk is fantastic and feels very good, or Elk even is a very search-first experience, trying to optimize for humans. But it is just an overwhelming amount of data, and doing log searches that take 40 seconds to retrieve are not impossible or even very hard to think of if you're doing things like petabytes a day. or even terabytes a day. So it's very possible just to be over your head with too much stuff to search through. And tracing, I would want to highlight, it's probably one of the newer methods in this and has also evolved a lot. There's been a lot of convergence between tracing and APM solutions. So they kind of are often talked about very similarly. And one of the major things that I think makes tracing much more approachable is just automatic instrumentation. That's becoming a standard across everything. So instead of going through your library and say, trace this, this is how you represent this, this is the tag you want, you just include a package and it does all of that for you. So there's a lot of great automatic instrumentation tooling there. And it's probably one of the best things to making tracing more accessible. And there's a lot of power to that. So just really want to focus on it's becoming significantly easier when I'm talking with people that say, have you thought about tracing? And they're like, yeah, it looked cool, but felt like a science project and I don't want to go touch my code again. It really has evolved and come a very long way to the point of like include jar, spit data here. Now we can actually start doing stuff with it. And I'll showcase some examples of that, but I'm just kind of highlighting, again, the tools that we have to understand this. Next point I really want to make is underlying to all of this is we are tasked with monitoring and understanding extremely deep systems, extremely complicated operations with tons of stuff going on. We want to make this as easy on ourselves as possible. I've previously worked with colleagues. One in particular stands out, Matthew Zier, or MRZ, was a big proponent of beach ops. Like, I don't want to be on call for dumb stuff. Like I want to focus all my time on automating these things away. And I want my life to be as easy as possible. If I can do my job from the beach, I'm doing something right. So being able to actually just make this debugging pattern as simple as possible really kind of appeals to us as humans. I don't want to necessarily be sitting at a screen and scratching my head all the time. I want to have this, aha, I did it. I solved the problem, on to the next one as fast as possible. And I have a background in cognitive science, so vision and learning and hearing are things that I've spent a lot of time studying. And I specifically love that backdrop to computer systems because ultimately computer systems need to appeal to people. People use computers. Computers don't really use computers that much. People use computers. So what happens within a computer needs to be very intuitive to a person. So there's a whole paper on UI and experience that I could go into, but in summary, people are very good at spotting visual differences. It's something they've evolved to do very well, from predator to prey to finding out what food is to being able to run and not trip over yourself. People are very just good at picking up visual differences. So it is very powerful having strong visualizations and representations of data to be able to make things very apparent. With the very data-driven, like ocean of data style debugging that we have, again, it requires a lot of very involved training. You have to learn how to read dashboards and then also learn what's noise, what's not, and kind of push things out of the way. So being able to appeal to your strengths and determining this and understanding what's going on is absolutely crucial. And being able to have something that someone can pick up and say, I understand that very quickly, as opposed to taking a week before they can even meaningfully engage in a conversation, is incredibly valuable. So core to that concept is having a strong working mental model of how your code's actually executing and what's happening. This, I think, is probably the biggest breakage in human understanding between metrics and logs and working with these really complex systems, because I, as a human, am thinking of the course of what failed in this transaction? How did this, as it goes through this entire system, where was the individual breakage? And it's kind of a sequential thing in my head. I'm following a thread execution, and it goes from one step to the next. Oftentimes, metrics and logs do not necessarily have that, and they're only concerned at each ingress and egress position within this, and they kind of look at it as compartmentalized individual steps. And that makes it rather difficult for us to track down because you can keep kind of following where the breakages happen, but you need a lot of your own interpretation into that to start getting meaning from. One thing that I've really taken to within tracing is it just kind of makes sense and follows my mental model of how code is executed. So things that we can start doing with this kind of data, I have a few screenshots up from, this is stuff we're doing in our product with some of this trace data, but I know very similar experiences are available with things like Zipkin and Jaeger and other tracing tools that are doing this. But being able to just very quickly highlight the difference and pull out any instances of change or differences in tags and isolating latency or error rates to those becomes pretty key in doing that. And just being able to highlight that in a way that is immediately obvious is extraordinarily powerful. I can't I can't overstate how important that is. And as much as it seems silly to engage with a tool based on the visualization or how things look, that largely does determine the experience that your users are going to have. And I cannot tell you how many organizations I've talked to that have problems with uptake of new systems because the system is hard to use. It's difficult. I can do the same kind of stuff anyways without learning a new tool. It might save me 30 seconds every other week, but why would I bother putting in the time for that kind of return? So it is absolutely critical having something that people actually can make sense of. And again, I'm advocating that tracing delivers that in a fairly obscure domain, typically. So just kind of showcasing what tracing delivers in this. A single distributed trace will actually follow the entire lifestyle of the request, whatever systems it hits. So in this kind of abstract, we can see that the trace is actually flowing through many different systems. And what we're actually given at the end of this is a full construct of what the request actually looks like. This style of chart is super common, and again, in every tracing tool, but this hamburger menu up at the top of where things are, stacked up and then happening sequentially is exactly what the code execution is doing. In this case, we color code different services. So every time the color change, there's a new service boundary. The black line up at the top is what we refer to as the critical path. And this is where CPU seconds are actually being spent spinning. Most of the time, other systems are literally waiting for a response or waiting for other work to be done. So the black line represents where that work is happening and really is a good way to identify where latency occurs and determine specifically what is going on in that individual component. We also have tags and metadata associated with this. This becomes super helpful as we're clicking through individual services. We can see what the requests look like at each stage. So you can say, before we sent this request, here's the state. This request received these HTTP headers, so you can quickly understand what was different between what was sent and what was received. And then also just get that full context of what's going on. And lastly, being able to actually attach logs to these traces is immensely helpful. Again, the problem with logs tends to be that there is so much data, but when the log hits exactly right, it is the exact thing that you need to see. You need to see that stack trace and the thing that the code actually tripped up on, because that's typically the best hint for you solving that problem. So having that immediately in context is extremely powerful. Again, just looking at this screen, we see a sea of red. There was an error that happened in this trace. Specifically, we see this call backend service that was happening, and there was an error fetching a specific ID profile. So being able to, again, see a problem that surfaced at like a Git profile view from a very high level, and isolate that there is, again, one service downstream that's causing these problems is extremely powerful. Especially, I'll dig into that a little bit further in another example, but I just want to really emphasize we can start changing how we're debugging, from sifting through a million of these, like describe node, describe pod, describe this, and stepping through each of the steps. Like, this system runs this. I think this one's next in the stack, so let me check that. Now let me compare and contrast 6 different terminal screens. That kind of change analysis is not easy for people to do typically, and it requires a lot of expertise and skill, which people build. Some people are incredible at this, but I would advocate that looking at something like this is way easier and something that you don't necessarily need to be a wizard to do. You can come in and see, just looking at this style of service diagram, or this representation of how data flows through systems, we can see that all of our top end users are experiencing errors. And they all go through our API gateway, and our API gateway has a bunch of errors. And then there's 2 individual services, the profile and a store server. These are each experiencing errors. The major benefit of this is oftentimes these systems will say, each individually report, I have an error, I have an error, I have an error. So you now have 5 or 6 different sources of alerts that are all screaming, we have a critical mass of errors, things are going wrong. And that mess of noise is kind of how you get desensitized to how alerts are coming in, and it's not, the user was able to just refresh the page and get through it, it's not blocking any progress, so like, it sucks to have errors, but they figured it out. Being able to quickly do this kind of resolution, and again, just click on show me this error. Oh, okay, it's several steps down in this trace, and it's this individual service that has an error, and that cascades everywhere else, and requests are failing because just one thing. Really fits my personal mental model of how code works, and how I assume other people envision code execution. And I cannot understate how powerful that actually is. Being able to understand where a problem's coming from and piece that together quickly is key to short-circuiting all of these firefight war room scenarios where you're coming in and trying to resolve an incident and get an RCA report ASAP. So some of the actual practical change queues that we should really be on the lookout for and start trying to optimize how we're catching problems and looking around them are change. Like change is the number one system to this. Oftentimes things like a change in user pattern is something that can be caught with an auto scale group, because if it's just a matter of like adding more bandwidth, then you can have something automatic addressed to that. However, system-induced change, things that your internal people are introducing to the system, whether it's new usage patterns or new stress or just bugs, are very difficult to track. And it becomes really critical to start following some best practices or enforcing that they are doing things like attaching version tags to everything. You need to be watching your golden signals for when you're actually, like, what is important and what does everything actually need to have as a minimum standard of data to be useful. So tracking things like errors, latency, throughput, and then additional metadata standards become absolutely critical. And again, just really re-emphasizing that this visual diagnosis is so key to humans understanding things quickly. Having something like being able to just visualize deployments alongside performance. In this case, we're just looking at how deployments track across different versions. Just mousing over this individual version, we can see that there's a canary deployment that we're slowly trying out with traffic. And in this case, we can see that about 75% of our traffic is going to the previous stable versions with about a 3% error rate. This new release that we cut has about a quarter of our traffic, but has 40% errors that are coming through. Massive red flag. And something that is immediately understandable, we cut a new release, it's this new version is tied to the increase in errors. Maybe we roll back and can dig into this service and look at that subset of data to understand what was going wrong in that case before we try to roll that out again. So being able to, again, have some level of data. Oftentimes this is just an environment variable to say, hey, what version of code am I on? But visualized in a way that makes sense and you can quickly draw conclusions from is extremely important. So getting to the question of whose fault is it anyways, and actually being able to point the finger at the appropriate person, it's almost always something new. Things tend to break when changed or when acted upon, and we need to be able to very quickly identify where change came from, what changes impacted, and what systems are actually experiencing the breakage when, especially in these very deep and complex systems, there's a lot of stress that is felt upstream and downstream from single breakage. So one service, again, might have this major upstream effect where everything starts crying error and gets stuck in retries and everything like that, when it really is just something lower level that has one problem instead of the 20 that we're seeing. So building this discipline and understanding that change breaks things, we need to start being able to answer these questions really quickly. How big of a deal is this? Is this something that users are basically, is this like, can I go back to sleep and deal with this in the morning? Is this something that I need to page everyone and say, hey, there's an active incident, like talk to customers, put up a banner on the site that says we're experiencing problems and we know about it, and then start very quickly answering the questions of why this happened, so you can start getting the right teams involved. So enacting this within your organization is going to be more of the call to action to all of this, how you can start doing these things, aside from optimizing for like visual diagnosis and having the right tools that you know how to look at. Being able to track how this change, having some control over this, and being able to revert change is extremely important. Being able to measure the change and also identify who did it is super, super important. Oftentimes, there's often a trick of like one service deployed a change, and that thing might have actually had a new version tag, but all the upstream systems didn't have a change because you're just touching the code base for one thing. And now you see a breakage experience all the way upstream and everything else is complaining with no apparent change. You just saw a spike and stuff, and you have to happen to look at that right individual service. So being able to actually identify it and standardize how that metadata is taken, or even isolate change and know who is pushing code at any given time, is super critical to that. And also central to this, I've said who's to blame or who did it several times, but the goal to understanding that is we need to understand who can actually fix this. Again, oftentimes our level of control and our visibility is limited by the tools in front of us. We need to be able to understand who can actually revert a given deploy or start introducing fixes that can address this, when pulling our usual handles won't necessarily address the problem. So it's a spirit of getting to an answer as quickly as possible, as opposed to being able to point a finger. So the last few thoughts I want to go over is how some companies I've worked with are actually putting this into practice and doing this in a meaningful way. This will vary pretty wildly, mostly by company size and evolution of their own monitoring practice and how much thought they've put into this. So there's three major patterns that I've seen when attempting to do this. The first being standardizing a monitoring package that every developer checks out or is just inherent in their code. This is something that they are expected to include in every release, with some standardized set of tracking versions, a set of monitoring, and a set of instructions that go out with this every single time. So when you respond to an alert, you pull up the page and it's like, take these steps to fix this. And you might not even need to do any diagnosis. It's like, if memory's high, this is something that happens with this service. Ignore it. But if it's been 10 minutes and memory's still high, try restarting the nodes. This is very, very powerful because it gives you a universal debugging experience. Anyone answering problems within the space can do the same thing and get meaningful results. A centralized but remote team can often answer problems about this. You don't need the individual developers to identify that there is a problem with their code. They often might be the person that's fixing it, but you can have someone come out and say, hey, I noticed you pushed a version of code here. This is individual log line shows up 6,000 times and is responsible for 6,000 errors. Address this when you get a chance, and we'll roll back in the meantime. The challenge that often comes with this model is you are responsible for maintaining a set of standards that is hopefully universal through your organization. Oftentimes, orgs have business units or groups that are very opinionated on how things should be done. So you can find yourself trying to convince internal parties that this is the right way. And also, anytime you change the central package, you now need to actually deal with the fallout. So it's kind of a almost a monolithic bit of code that needs to be able to support all of your older and previous versions. If someone introduces a new language or if someone introduces a new technology, that creates extra work for these people. So that's one of the trade-offs and why you need full-time staff doing this kind of work. Next way that I've seen this really addressed is having a centralized platform team. This is something that I, again, see probably medium to large scale companies doing. So you'll have something like a platform as a service where developers can just subscribe and say, I want 1,000 gigabytes of RAM and a petabyte of disk. And the platform team will go off and make it so. And then they just have access to those resources. This is fantastic because it abstracts a lot of this away from the developers, and the central platform team has even more tools and levers to be able to control what's happening within their environment. You can build very specific and automated workflows and be a little bit more declarative with this is how the platform works. A new requirement of your engineering is designing your systems in a way that is compatible with my platform. So you can give a little bit more structure to how they're working. And you often have a lot more visibility into where breakages occur because you have so much more control. The major problem with this is you are now providing a service to customers, and you have the friction of my customers want this, but the best way I can provide my service is that way. And now you're kind of fighting with your engineers to create your platform as stable as possible. You're measured on your SLOs, whereas they're measured by the amount of change that they can introduce, the number of features, the amount of improvements that they can bring to the system. So you're not necessarily measured in a synergistic way with your development team. And oftentimes the platform teams have the attitude of, I don't need to know what's running on my platform. I don't care about the code that's running on my platform. You make it work with my platform. And that is, again, a strong sense of enforcing standards, but it does have some contention between how the developers are running and also serves as a blocker for the on-platform team's ability to understand specific problems that are happening. Their concern then becomes like, let me assign blame as fast as possible so I can tell you to go fix something, as opposed to I can volunteer what needs to be done. Whereas your hands might be on the keyboard, I can say, hey, here's the specific thing. Resolution in this often says, I told the team to fix, there's a problem with you and fix something. And of course, there's always back and forth with that. It wasn't me, it was this team. No, it was that team. So there's, again, just kind of a culture model that you need to fix in there. The final model that I've really seen a lot of teams take, and this has definitely been more of the smaller company style, especially in like the startup realm and observability teams that I've seen. They'll have explicitly DevOps teams that work alongside, and this is typically an embedded engineer that works alongside other software like feature engineers that are working on releasing code. And the DevOps engineer works alongside them in the same sprint cycle to ensure that automation cases for remediation are being written. The quality of data is being is high for the teams that are submitting new code, and that resolution pathways are included with any new release. So through testing, they found introduce stress to the system, found ways that it breaks, and offer both automated and more manual solutions that can be done to fix this code when it breaks. So you're able to pick up a manual every time a specific thing breaks and have it tailored fix experience for you. The problem with this becomes really difficult to scale and expensive to maintain, having someone that's embedded explicitly to do this. Oftentimes this takes the shape of a QA engineer trying to actually build in automated test cases and take on a DevOps hat, or the developers themselves just having higher mandates to submitting their code. There's higher levels to entry, so that slows them down significantly, and it's something they don't necessarily have an expertise on. You want your software engineers to have a very deep understanding of how to get features out and how to improve your platform, not necessarily spend a lot of time on the latest and greatest and having counters versus gauges and this tracing technology versus that one. It's something that's peripheral to their real job of getting features out the door. So those are the most common ways to actually structure your organization to start solving these problems and doing things well that I've seen. But again, I really want to emphasize that at the end of the day, you as a person is the consumer of these systems. You need to make things that are easy for you to understand. Again, I'd emphasize having things that are optimized for novice users, having very visual-driven debugging that highlights any change in breakages and links change to breakage, because that often is the case. And make sure that you're doing stuff that you are good at. I know the notion of the 10x engineer actually might even be an old thought at this idea, but having the people that are just like wizards reading the Kubernetes outputs and know exactly which pod to describe and can read the right error log and pick out the specific thing, that looks like wizardry and is something I think we would all love to be able to do and do well. But that level of expertise is simply just hard to do, and oftentimes not necessary or helpful for everyone to have. Not everyone can be that extremely deep expert in the system, but you do need to allow other people to contribute and not have that extremely high barrier to entry to be useful in a debugging situation. So design so everyone can be useful, not just the super genius wizards that know the entire system. And that is the end of my talk. I'm happy to move into Q&A and accept any questions that anyone has.
Adam, so thank you very much for that great presentation. There are two questions that came in through some different channels for you. If you want to click over to the new on Q&A and hit that first question.
Yeah, so the first question is, what would you say are the main advantages of OpenTelemetry over other open source solutions, like other tracing and metric solutions like Zipkin, Dropwizard, or Micrometer? One of the major benefit is OpenTelemetry is getting a ton of attention, getting a ton of development. All of these different organizations are working on it. So there is a lot of inter-vendor and inter-company cooperation on this. Also, the scope of OpenTelemetry is to be able to capture metrics, logs, and tracing data all in a single package. So now you have this centralized telemetry pipeline that you're able to just shoot at whatever system you think is most useful. So this gets you away from vendor lock-in of having to say, I'm tied into their pipeline and I like the data that this agent gets better than that one. So I'm basically buying an instrumentation tool rather than an insights tool. I think that is a major step in the right direction so that you can start standardizing data you collect. You can start being more flexible with how you're analyzing it. And the emphasis with this, or the really valuable and cool monitoring tools that I've seen, are ones that offer insight on your data and tell you where to look, as opposed to, here's an endless hole, feel free to search any query. We have a super cool query language so you can figure stuff out. I, as an operator, don't want to figure stuff out. I want to be told what's going wrong, and then focus my attention on how to fix it. So oftentimes, a lot of this data for the sake of being able to slice and dice it in a million ways is cool, but not practical from a business sense. So I think that's probably one of the most exciting things about OpenTelemetry, and how much like Splunk and Google and Microsoft and everyone is working on this. So other competitive vendors are all in the same boat here.
And Adam, before you get to the next question, I just wanted to share, if you could share your email address for everybody, or any other channel that you would like the attendees to communicate with you directly if they had additional questions about Lightstep and what you guys are doing. Could you give us your email address real quick?
Yeah, absolutely. ajohnson@lightstep.com.
All right, great. And so we have another question.
Yeah, so the question is, some organizations feel that understanding orchestration, or Kubernetes, is the responsibility of operations, but not something developers need to worry about. What type of understanding of Kubernetes do you think devs should have? This kind of ties into the trying to abstract the platform away from code, and I understand how the industry is really pushing towards that. I want to be able to just purely write code and release features, and I don't care where it goes, whether it's a VM or Kubernetes. And practically, that is very difficult. Again, you're just put in this situation. I'll harken back to that little pyramid diagram, if I slide back in the right way, where you now have a layer of control over way less than what you're responsible for. So you can control platform things, but there's so many other things going on underneath. It's really crucial for people to understand what is good and what's not, and what usage patterns are good and what's not. You really need to be able to understand how things are scaling and how things are breaking. So my minimum level of recommended understanding is you need to understand how big or small you need individual nodes. You need to understand how long or short they're going to be alive and optimize for your company's container lifecycle pattern. And you need to be able to basically leave enough breadcrumbs and visual cues that anyone coming into the system can start answering meaningful questions against it. So you need to understand that your code level needs to emit enough information and hints that someone coming in and says, like, the container looks fine, CPU's fine, memory's fine, and the node's not complaining, but things keep failing. You need to give enough information that an operator in your system can do something about it. So the more understanding, the better. And I totally get the pie in the sky, like, software is software and it should be pure and run anywhere. But that's simply not reality. Again, super easy parallel is, do you need to understand a JVM when you're writing Java code? And the answer is 1000% yes, because if you don't understand how memory is being utilized, you might just write a completely unusable program that does really cool stuff, but just doesn't work. So yeah, there needs to be reasonable understanding of how things work so that you can leave informed breadcrumbs and pick things up later.
And Adam, it looks like we have one other question.
Mm-hmm. And the new, is it best to use one tool that gives you tracing metrics and logging, or should you select a tool for each? And I've seen a lot of mixed opinions on this. Oftentimes, I have seen probably the most successful and the most advanced companies using a best-in-breed tool for each of these and getting, again, that immediate analysis. Typically what you're after, or what I'm really advocating for, is having a tool that will advocate and bubble up for you the change in the system and what's going wrong, as opposed to just one place that I have this limitless depth of information that I can sift through if only I knew the right incantation to say. That ocean of data tends to be a lot less valuable than a best-in-breed tool that can give you a specific answer. This often, I know this often comes up, and this is like a procurement-driven decision, not a practical systems decision, where we can save some money and make it easier for our procurement team and process if we just cut one check instead of 3 or 4. So I understand that process, but again, I think you really need to measure the value that you're getting and the amount of training and work that goes into getting anything meaningful out of these systems. The thing that this like super parallels for me, I worked a bunch on Hadoop systems, and everyone was like, oh, we're moving into data lake, we're moving into data lake. And now that's like an absolute dirty word, because people threw all of this stuff on HDFS. It's like, what do we do now? Like, it's there, but no one can find anything. So it's kind of useless. We're in the same boat as before. We just now have one search bar that never loads and never gets the right thing, as opposed to 30 different systems where I can't find the right machine. So focusing on the answers that you're trying to get, whether it's keep a system up or show me the right file, are pretty shared in that distributed computing world.
All right. Well, it looks like that's the last question. Just a couple of notes. Again, Adam, throw out your email address again.
ajohnson@lightstep.com.
Thank you very much. We did have a question before. I did delete it, but I just want to bring it up that this session has been recorded. It will be made available in the next 24 to 48 hours, and will be emailed out to the attendees of the event, as well as those who may have showed up late or didn't have a chance that registered but that couldn't come. So we're going to be doing that. This can also be found and will also be found in our archive at devnetwork.com. We have all of our webinars archived there. There's a previous webinar from Lightstep as well there. And we have a wide variety of content, in some of them in relation or regards to Kubernetes. So for additional learning opportunities. So just wanted to say thank you to all. Thank you, Adam, for such a great and energetic presentation. And we look forward to having you speak again. And we want to thank everybody for participating in today's webinar and have a great and safe day.
Thanks, everyone.